To this point, we've talked about group theory, we've talked about Burnside, which was one way for us to come up with equivalence classes, and now we're going to look at Polya's method of enumeration, which is essentially another way to come up with what we found using Burnside's theorem, which is the number of equivalence classes. So let's look back, and this slide should look familiar because I used it in a different video. We're looking at a square with numbered vertices, and we're looking at rotations. So a 0-degree rotation, and again, it doesn't matter if you go counterclockwise or clockwise. In this example, I've gone counterclockwise. So obviously, if I'm not moving, 1 maps to 1, 2 maps to 2, 3 to 3, 4 to 4. And we talked in 16.1 how to get the cycle decomposition, which is a product of disjoint cycles. If I go 90 degrees, 1 maps to 4, 2 maps to 1, 3 maps to 2, and 4 maps to 3. And then again, how did I get from here to here? I said 1 goes to 4, 4 goes to 3, 3 goes to 2, 2 goes to 1. Once 1 goes back to 4, that's when I know I can essentially stop, once I end up back at 1. I did the same for 180 degrees, or pi, and then 3 pi over 2, or 270 degrees, gives me 1, 2, 3, 4. So hopefully we remember that from when we went through it in 16.1, or just because we just went over it again. Now what we did not do in section 16.1 is do the same for reflections. We just focused on rotations just for simplicity, but let's go ahead and look at it for reflections. And notice I've called horizontal R1, so if I reflected over this line, 1 would map to 4, and 4 would map to 1, 2 would map to 3, and 3 would map to 2. So that's my cycle decomposition. If I'm doing the same thing, but now I'm going for R2, 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. And then looking at R3, which is this diagonal, 2 goes to 2, 4 goes to 4, 1 goes to 3, 3 goes to 1. And lastly, the other diagonal, 1 goes to 1, 3 goes to 3, those are fixed. And then 2 goes to 4, and 4 goes back to 2, because we're reflecting across that line. So here's my cycle decomposition. So I've got all of my rotations, I've got all of my reflections. What am I going to do with those? Well, in this case, looking at Polya's method, I'm essentially going to be looking at the number of distinct colorings, which is code for orbits or equivalence classes, which is code for the exact same thing that you just found using Burnside's theorem. What I'm going to do now is I'm going to, again, use G as my permutation group, M is the number of colors, and cycle index will have to do with how many cycles and of what length. So let's take a look at that example we just went through. We're going to look at when we didn't do anything, 1 map to 1, 2 map to 2, 3 map to 3, 4 map to 4. So I have 4 cycles of size 1. For pi 1, which was 90 degrees, remember this is what I had. I had 1 4 cycle. So I had 1 cycle of length 4. For pi 2, which was the 180 degrees, I had 1 goes to 3, 3 goes to 1, 2 goes to 4, 4 goes to 2, so I had 2 cycles of size 2. And you get the idea, is really I've just copied all of my work from the last 2 pages, and I've written it using this crazy little notation here. This one says, hey, I've got 2 cycles of size 1, and I've got 1 cycle of size 2. So all I'm going to do is I'm going to then say, well, let's talk about the number of colors now. Well, I used 2 colors. So before I got to this point, let me digress just a little bit. Here I've just listed all of these. Then I said, okay, well, let's consolidate if I can. I've got one of these. I've got an X14 and an X14, so total I have 2 X14s, which means cycle, or one quantity of cycle length 4. I've got 2, 2, 2, that's 3 of those. And then these guys, I've got 2 of those. So that's where this came from. Now all I'm going to do is I'm replacing the X sub 1 and the X sub 4 and the X sub 2 and the X etc. with 2's. Now why am I doing that? Because there are 2 colors. So 2 to the 4th and 2 from here, and then X sub 4 becomes 2 to the 1st. And this is 3 times 2 to the 2nd, and this is 2 times 2 to the 2nd, 2 to the 1st. And what happens? Well, I get 16 plus 4 plus 12 plus 16. I'm averaging that, dividing it by 8 essentially, because the G was 8, just as it was before. And guess what? I get 6. Now, if you'll recall from watching the Burnside's theorem video probably a few moments ago, my solution was also 6. Let's do a new example. This is still a square, so I still have same G. I didn't make you come up with a new G. 0 degrees, 90 degrees, 180, 270, and then the 4 different reflections. So let's look at them step by step. I have a 3 by 3 square with 4 colors, so that 4 is going to be my M that I'm going to use later. But let's take a look at pi 0. What's going to happen at pi 0? Well, everything's going to remain exactly where it is. So I have 9 of size 1. For pi 1, which means that I'm rotating 90 degrees, again, clockwise or counterclockwise doesn't matter. If I'm going this way 90 degrees, and again, I'm not looking at vertices, but instead what's on the inside, the only thing that's really going to remain the same is 5 is going to go to 5, right? 1 is going to go to 3, 3 is going to go to 9, 9 is going to go to 7, 7 is going to go to 1. So that's a 4 cycle. 2 is going to go to 6. Let me use a different color. 2 is going to go to 6, 6 to 8, 8 to 4, 4 to 2. And then 5 is going to remain right there in the middle, all by himself, where he was before. So how would I write that? I would say I have 2 cycles of size 4. So remember, the size goes on the bottom, and the number of cycles goes on the top, and then 1 cycle of size 1. Now let's take a look at 180 degrees. What's going to happen? 1's going to go to 9, 9's going to go to 1. 2 is going to go to 8, 8's going to go to 2. We get the idea. We're going to have a lot of 2 cycles. Things are going to switch places. Again, what remains the same? The 5 in the middle. So I have 4 cycles of size 2 and 1 of size 1. Now let's look at 270. Well, 270 is going to look just like pi 1. These are going to be really similar, just a little bit different. So now, instead of 1 going to 3 and 3 going to 9, now I'm essentially going the opposite direction. Or 1 goes to 7, 7 goes to 9, 9 goes to 3. You get the idea. But it's the same idea. I've got a 4 cycle, a 4 cycle, and a 1 cycle. So I've got 1 of size 1, 2 of size 4. Now let's take a look at reflections. Reflection 1 looks like this. So 1 goes to 7, 7 goes to 1, that's a 2 cycle, 2 goes to 8, 8 goes to 2, 3 goes to 9, 9 goes to 3. So I've got 3 2 cycles, and then 4 goes to 4, 5 goes to 5, 6 goes to 6, so I've got 3 1 cycles. So 3 2 cycles and 3 1 cycles. Same thing essentially is going to happen going this way. 1 goes to 3, 3 goes to 1, 4 to 6, 6 to 4, 7 to 9, 9 to 7, 2 to 2, 5 to 5, 8 to 8, so it's the same notation. And then we look at the reflection across diagonals. Let's look at this one. 1 goes to 9, 9 to 1, 2 to 6, 6 to 2, 4 to 8, 8 to 4, 3 to 3, 5 to 5, 7 to 7. And we can tell that that's going to be the same thing for the other diagonal as well. So how do I put all of that together? Well, again, G is 8, so it's going to be 1 over 8. And then I'm going to replace x sub whatever with what? With 4. So how does that look? I've got this guy was G. I just recopied what I had before. I consolidated a little bit. I said there were 2 of these and there were 4 of these. But then notice all I did was replace this with 4, 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 and this with 4. So this is my final answer, or I went ahead and multiplied it all out because I kind of like to have an answer sometimes. So 1/8 of that gives me 34,960. If you've already watched the Burnside video, which I assume you have, we did this question right at the end. We said we've got an equilateral triangle, we've got 4 colors that we can choose from at each vertex, maybe not tokens, but you get the idea. That would be a funky little token. But 4 colors I can choose from, and how many ways can we color the vertices? Previously, using Burnside, we came up with 20. So what I'd like you to do is use Polya's method to, again, hopefully come up with 20. When you're done with this question, press play to see how you did. So obviously, first and foremost, you need to come up with G. G being, in what ways can I rotate this figure? So I've got a rotation of 0, a rotation of 120 degrees, a rotation of 240 degrees, and to 360 would be back to 0 again. Then I have already marked R1, R2, R3, which is essentially going through one vertice and the opposite side. So I've got 6 different ways that I can rotate or reflect this figure. Based on that, I have come up with the disjoint cycles. If I don't do anything, 1 maps to 1, 2 maps to 2, 3 maps to 3. So that's 3 of cycle length 1. If I rotate essentially 120, again, 1 goes to 2, 2 goes to 3, 3 goes to 1. Now I'm back to where I started. I've got 1 of cycle length 3. If I'm going to 40, then 1 goes to 3, 3 goes to 2, 2 goes to 1. Again, 1 of cycle length 3. Let's move on to the reflections instead, using R1. 1 goes to 1, and then 2 goes to 3, 3 goes to 2. That's 1 of cycle length 1 and 1 of cycle length 2. And it's going to be similar for all of the other reflections. For here, 2 goes to 2, 1 goes to 3, 3 goes to 1. And then for my last one, R3, oh, that was R3, sorry about that. I think I switched those around. For my last one, 3 goes to 3, 1 goes to 2, 2 goes to 1. We get the idea. So what do I end up with? Well, I've got 1 divided by 6 because G is equal to 6. The number of elements of G is equal to 6. And then I'm writing this out. Then I'm consolidating if I can. So if you'll notice, these 2 are the same, so I've just said there's 2 of them. These 3 are the same, so I've said there's 3 of them. And now I'm replacing x sub anything with the number of colors. So this becomes 4 to the third, because this becomes 4. X sub 3 becomes 4, so 2 times 4 to the first. And then x sub 1 becomes 4 to the first. And x sub 2 becomes 4 to the first, so 3 times 2 fours essentially. And guess what? I end up at 20. And of course, just one more to try. Again, this question should look familiar. This is the chessboard problem that we solved using Burnside. I want you to now use Polya. When you're ready, press play to see how you did. Alright, well, we've got G, which we've used a ton because we're using squares a lot. So I still have 4 different rotations and 4 different reflections. I've looked at the cycle notation. If I don't move anything, 1 to 1, 2 to 2, 3 to 3, etc. I'm going to have 16 total of size 1. If I'm going 90 degrees, 1 to 4, 4 to 16, 16 to 13, 13 to 1. And again, notice I've just written that out for you. So I have 4 of cycle length 4. If I'm looking at 180 degrees instead, I'm really just doing a lot of flip-flops. 1 to 16, 16 to 1. 2 to 15, 15 to 2, etc., etc. What I end up with is 8 of cycle length 2. So I've got a 16, I've got 4, I've got 8. If I'm doing this guy, I didn't go ahead and write out the permutations, but again, it's the same idea as pi 1, which is the same solution. 4 of cycle length 4. For R1, again, looking at this, I've got a lot of just flip-flopping, and that's going to be the same for R2. So R1 and R2 are both going to be 8 of cycle length 2. And then if I look at R3 and R4 are going to be the same. Again, that's looking at a diagonal. That I'm going to have 4 of cycle length 1, so 4 that reflect onto themselves. And then the rest of them are just going to do some flippy floppies is what's going to happen. And so I've got 4 of cycle length 2 and 4 of cycle length 1 and 6 of cycle length 2, which I've consolidated down here and replaced with, because there are 2 colors, replaced with 2s. Then I found my solution, which, yes, you guessed it, is the same solution we found using Burnside's. Good work, everyone.